just a poor boy, though my story is seldom told. I squandered my resistance for a pocket full of mumbles, such are promises. All lies and jest, still a man hears what he wants to hear.
Okay, section 5.5 is called a procedure for curve sketching. And good news, there's only one question to do here. But hold on, it is the biggest question you will ever do in high school math. We're going to sketch a curve, and it's going to be a complicated curve, and you're going to go through all these steps before you actually get to the curve. So there's a lot to write down here. To start, you're going to have to take a whole bunch of notes. Ready? Here we go. When you're going to sketch these curves, you have to figure out the following things. You have to figure out the domain. So when you're worried about domain, there's two things that you really want to look out for. You want to look out for square roots, because when you have a square root, you need to make sure that the radicand, the part inside the square root, you need to make sure it's positive or equal to 0. So for example, if you were graphing this, you would need to ask yourself, what is it that makes the radicand is the stuff inside the radical, what makes that radicand greater than or equal to 0? Okay, the other thing you have to watch out for domain is when you have denominators, because of course your denominator can't be equal to 0. So if you had y equals 1 over x minus 1, you'd have to ask yourself, what is it that makes this denominator equal 0? And that would not be part of the domain. Okay, intercepts. We've talked about intercepts already in this chapter. If you're looking for y-intercepts, if you're looking for x-intercepts, set y equals 0. And if you're looking for y-intercepts, set x equal to 0. And then solve. Or evaluate if you're looking for the y-intercepts. Okay, symmetry. We've talked about symmetry before. There's two types. It's even symmetry if f negative x equals f of x. And remember, in such a case, it's symmetric about the y-axis. So it's like a mirror right on the y-axis. And we say it's odd symmetry if f of negative x equals negative f of x. And that's symmetric about the origin. Remember, that's when you turn it upside down, it looks exactly the same. Okay, asymptotes. There's two different asymptotes, actually three, but we'll get to the third type in a next section. There's vertical asymptotes, and this is whenever the denominator equals 0. And you have to remember that when you do find a vertical asymptote, you also want to look at what happens on either side of that asymptote, whether it's tending towards infinity or negative infinity. So remember, if x equals a is the vertical asymptote, what you'll need to find is the limit of the function as x approaches a, that's an arrow, x approaches a from the left, and you'll also have to find the limit of f of x as x approaches a from the right. For horizontal asymptotes, we said that y equals L is the horizontal asymptote. That'll be the equation of the horizontal asymptote if the limit of f of x as x approaches infinity equals L, or if the limit of f of x as x approaches negative infinity equals L. So in order to figure out the horizontal asymptotes, you're going to evaluate the limit as x approaches infinity and negative infinity. Okay, intervals of increase or decrease. Well, we've been doing that for a while. That's the first derivative test. You're going to calculate the first derivative and then find the critical values and place them on a wiggle graph and check out the different intervals to see whether it's positive or negative. For local maximum or minimum, you have two choices. My idea of what to use would be the first derivative test, because you already have done this. All you'll have to look to do is see if it goes from increasing to decreasing, in which case it's a maximum, or decreasing to increasing, in which case it's a minimum. Or you could also use the second derivative test, which we talked about last day. Concavity and points of inflection. Well, to do that, you are going to have to find the second derivative. And then remember, if the second derivative is greater than 0, then it's concave up. And if the second derivative is less than 0, then it's concave down. And you get inflection points when it goes from concave up to concave down, or when it goes from concave down to concave up. And finally, after all that, you're going to sketch the curve. Now, when it's time to sketch the curve, what I recommend is you draw asymptotes as broken lines. that you sketch the portion of the graph near the asymptotes. Remember, that's when we'll figure out whether it's going up towards infinity or towards negative infinity or whatever. You plot the intercepts, the x-intercepts, the y-intercepts, plot the maximum and minimum points, plot the inflection points, and then you can finally draw the curve. Okay, got all that? Great, you're ready to do one question, and here it is. Sketch the curve y equals 3x to the fifth minus 5x cubed. We're going to follow all the 8 steps listed on the front of this page, and we're going to get a sketch out of it. So the first thing it says to do is to look for the domain. And for domain, specifically, I said to look for whether there's a square root in the function. There's not. Also to look whether there is a denominator in the function with a variable in the denominator, like an x in the denominator. There's not. So what does that mean? This means that the domain x is an element of all real numbers. Anything works. You can put any number into these x's here and it will work. Any real number. Okay, the second thing we wanted to do is we want to look for y-intercepts. So in order to get the y-intercept, we're going to plug into these x's, we're going to plug 0. So you get y equals 3 times 0 to the fifth minus 5 times 0 cubed. Well, that just equals 0 minus 0. So our y-intercept is 0. And for x-intercept, we have to solve, right? We got to plug 0 into the y. So we get 0 equals 3x to the fifth minus 5x cubed. So let's factor out a x cubed. And that'll leave you with 3x squared minus 5. So that means that either x cubed equals 0 or 3x squared minus 5 equals 0 or both. Well, solving this is easy. It's just x equals 0. Solving this, a little more difficult. Let's move the 5 over. Let's divide by 3. And then we have to take the square root. And also, since we're solving with square roots, we have to put plus minus. So plus minus the square root of 5 over 3. Okay, so let's actually write down what we know here. We know that the intervals are 0, 0, and this is also 0, 0. It's the same thing, right? Whether you look at this as an x-intercept or y-intercept, it's both. 0, 0 is 1. Okay, the other intervals are root 5 over 3, 0, and negative root 5 over 3, 0. And the other thing you might want to do, might as well do it now, you want to get a sense of just how big is root 5 over 3. So take your calculator, put 5 divided by 3, take the square root, and you're going to get approximately 1.25, and obviously negative 1.25 here. Okay, that's it for intervals. Let's go on to step 3, which is whether it's odd or even symmetry. So what we do for that is we put, wherever we see x, we're going to put negative x. So get y equals 3 negative x to the fifth minus 5 negative x to the third. If we simplify that, we will get, well, this is 5 negative, so it's going to stay negative. So we're going to have negative 3x to the fifth. This is also 3 negatives, so it's going to stay negative. So we have negative, negative, it's plus 5x cubed. Now, is that exactly the same as what we started up here? No. Is it the negation of this? Yeah. This is exactly what we have here, but negative, negative. So this is opposite, which means negative f of x equals f of negative x. So this is odd symmetry, which means it's going to be symmetric about the origin. You're going to be able to turn your graph upside down and it's going to look exactly the same. Okay, 4, we're looking for asymptotes. So first let's look for vertical. Vertical asymptotes occur whenever the denominator equals 0. Well, there is no denominator here, so we would say none. Horizontal asymptote. For horizontal asymptote, we want to see what happens when we plug infinity or negative infinity into this function right here. So let's figure out the limit of this function, but let's start by factoring out an x cubed, just like we did here. So we have x cubed and then 3x squared minus 5. Let's do that. So x cubed, 3x squared minus 5. We want to know the limit of that as x approaches infinity. Well, infinity cubed is definitely going to be a huge number. I'll put a big positive because it's going to be a big positive number. And then x squared is obviously a huge amount because it's infinity squared, huge amount, times 3, still a massive amount, and subtracting a whole 5. That's nothing at all, really, right? So this is a big number times another big number, Well, a big number times a big number equals a massive number. In fact, how big is it? We're going to call it infinity. So that means there's no horizontal asymptote when we approach infinity here, because this has to be like a number, a real number. Infinity doesn't work here. Okay, let's look at the limit as x approaches negative infinity. So we do the same thing, have this factored, 3x squared minus 5 equals, okay, negative infinity cubed, well that's still going to be negative, 3 negatives, so it's going to be a big negative. And then x squared, well that's going to be massive positive because you're squaring, times 3, still a massive positive, take away 5, still a massive positive, so we have a big positive. So when you multiply those together, you get negative infinity. Okay, so there's no horizontal asymptote, but this was still very useful to do this, because now we know that as x approaches infinity, as x gets really, really big, it's going up towards infinity. We know as x goes down towards negative infinity, as x gets really, really small, it's going down towards negative infinity. So it's still very useful information. Okay, step 5, we're finally able to start taking derivatives and stuff. So we're going to take the derivative of this. So y prime equals 15x to the 4th, and then bring this 3 down, 15x squared. Y prime equals 15x to the 4th minus 15x squared. Why don't we go ahead and factor right now? You could take a 15x squared out of here. So at 15x squared, you're left with x squared minus 1. And you could even factor the part in brackets. You have 15x squared, and then x plus 1, x minus 1. So this is the derivative in fully factored form right here. Now what we want to do is we want to find the critical numbers. How do we do that? We look to see what would make this, when would this not exist? It always exists. What would make it equal to 0? Well, this will be very fast because it's already all factored. 15x squared, x plus 1, x minus 1. When does that equal 0? Well, when x is equal to 0, when x is equal to negative 1, and when x is equal to 1. So those are the numbers we're going to put on our wiggle graph. And we're going to check these intervals. Where are we going to check them? Right here. Notice this first one's squared, so it's always going to be positive. So you actually only need to check these two right here. So let's do that. Start up here. I'll do 2. 2 plus 1, positive. 2 minus 1, positive. Positive times positive is positive. That means this is increasing. Between 0 and 1, I'll pick a half. Half plus 1, positive. Half minus 1, negative. Positive times negative, negative. So this is decreasing. Negative 0.5. Negative 0.5 plus 1 is positive. Negative 0.5 minus 1 is negative. Positive times negative is again negative. So it's decreasing here as well. And below negative 1, how about negative 2? Negative 2 plus 1, negative. Negative 2 minus 1, negative. Negative times negative is positive. So it's increasing here. So here's our areas of increase and decrease. I guess we could write them down here if you want. For increase, it's from negative infinity to negative 1, as well as from 1 to infinity. For decreasing, intervals of decrease, it is from negative 1 to 0, as well as 0 to 1. It does not include 0. Okay, step 6 is our local maximum and minimum, and we're ready to do that right now. We can actually just put down max, min, remembering these are local maximum, minimum. How come we can do that? Because we just look at the increase and decrease. It goes increase and then decrease. Well, that's a maximum. So we have a maximum at the point negative 1, comma, something. We'll figure that out in a second. Decrease, decrease. No, there's no maximum or minimum there. Decrease, increase. Yeah, there's going to be a minimum there. So we have a minimum at 1, comma, something. So how do you figure out the y values here? You plug those into the initial function. So you're going to have to find what f of negative 1 is and also f of 1. So let's do that. Go back up here. I know it says y, but you know that means the same as f of x, right? So you just plug in 1 and negative 1 into there. Let's do 1 first. So we have 3 times 1 to the 5th, and then minus 5 times 1 cubed. So 1 to the 5th is 1 times 3 is 3, 1 cubed is 1 times 5 is 5, 3 minus 5 is negative 2. So this point is at 1, negative 2. And the other point, if we put negative 1 in there, you get 3 times negative 1 to the 5th minus 5 times negative 1 cubed. Negative 1 to the 5th is negative 1 times 3 is negative 3. Negative 1 cubed is negative 1 times negative 5 is plus 5. So you get 2. So negative 1, 2 is your maximum. So lots of important information here. Okay, step 7, we need to find the concavity and points of inflection. So we have to take the second derivative. So we'll look back up here, and I would look right here if I was you to get the second derivative. So y double prime equals, bring the 4 down and multiply, you get 60 x cubed. Bring the 2 down and multiply, you get negative 30 x. And once again, let's go ahead and do the factoring right away. Put it in factored form. So factor out a 30x, and you're left with 2x squared minus 1. Now, if you wanted to, you could use the second derivative test, right? And you could plug negative 1 and 1 into both of these x's and see whether you get positive or negative amounts. If you get positive amount, that means you have a minimum, and if you get a negative amount, it means you have a maximum. But we already did that information. We got that information when we did this right here. So up to you, but you could have waited till now to get the maximum minimum if you wanted to. So let's find our pips, our potential inflection points. When do we have those? When this does not exist, but it always exists, or when this is equal to 0. So 30x times 2x squared minus 1 equals 0. That means either 30x equals 0 or 2x squared minus 1 equals 0. When's this equal 0? When x is 0. To solve this, move the 1 over, divide by 2, and then take the square root, and again you have to put plus minus. So plus minus the square root of 1/2. You can actually simplify that a little bit because you can take the square root of 1. Square root of 1 is 1, and then you still have the square root of 2 on the bottom. So those are the numbers you're going to put on your wiggle graph. We have got 0, 1 over root 2, and negative 1 over root 2. And again, you're going to have to get a sense of how big these amounts are, 1 over root 2. So take your calculator, divide 1 by root 2, and if you do that, you'll find it is about 0.71. Okay, let's test these out. We're going to plug them into here, and we want to see whether it's positive or negative. So a number bigger than 0.71, how about 5? 30 times 5, positive. 5 squared is 25, times 2 is 50, minus 1, definitely positive. Positive times positive is positive, so that means this is concave up. A number between 0 and 0.71, how about a half? So 30 times a half, or 0.5, is 15, that's positive. A half squared is a quarter, and 2 times a quarter is a half, and half minus 1 is negative. So you got positive times negative, which is negative. This is concave down. Okay, a number between 0 and negative 0.71. How about negative a half? 30 times a negative half is negative. Negative half squared is positive quarter. 2 times a quarter is a half, and a half take away 1 is negative. So you got a negative times negative, which is positive. So this is concave up. And something below negative 0.71. So how about negative 10? 30 times negative 10 is definitely negative. Negative 10 squared is 100, times 2 is 200, and take away 1 is 199. It's definitely positive. So negative times positive is negative. This is concave down. So we can put our areas of concave up and concave down. It's concave up between negative 1 over root 2 up to 0, as well as from 1 over root 2 to infinity, and it's concave down from negative infinity up to negative 1 over root 2, as well as between 0 and 1 over root 2. And now what we can get is our inflection points. So where do you look for that? You look for the way there's a change in the concavity. So concave down and then concave up. This is an inflection point. So there's one at negative 1 over root 2. Positive to negative. Yep, there's going to be an inflection point here. 0 comma something. And 1 over negative to positive. So there's going to be an inflection point here. 1 over root 2 comma something. So what do we have to do now? We got to plug those points into the original. Well, the 0 is easy. We already know that point actually. We got it right here, 0, 0. So we've got that. Now for this, I think probably what you want to do is you just want to plug 0.71 into all these x's here and get what the value is. And if you do that as a decimal, you're going to end up with 1.24 here and negative 1.24 there. You can do it by plugging 1 over root 2 into all the x's, but it is a bit complicated. And this is fine for me because when you graph it anyway, it's going to be more useful to have it as a decimal answer like this. Okay, we're now ready to graph this. I don't know if you have any room left. You probably ran out of room a long time ago, but we're going to try graphing this right here. And if we look at some of the points we're interested in, we have 0, we have 1.25 and negative 1.25, we have negative 1, we have 1, we have 0.71. There's nothing really bigger than 1.5. So I'm just going to go 0.5, 1, 1.5, and negative 0.5, negative 1, and negative 1.5. In terms of y values, how high do we go up to? 1.24, 2, and negative 2. I think those are the biggest ones. So I'll go 1, 2, negative 1, negative 2. We're all set up to graph this. Okay, we have no asymptotes to draw, so we don't have to worry about that. So we're going to put our intercepts on. Remember, our intercepts were at 0, 0, and then 1.250 and negative 1.250. Okay, we're going to plot the maximum minimum points. Well, we have a maximum at negative 1, 2, so that's right here, and a minimum at 1, negative 2, which is here. And then our inflection points, we have one at 0, 0, we've already got that one, and then we have one at negative 0.71 and 1.224, so let's see, that would be around here, and we have another one at positive 0.71 and negative 1.24, which would be somewhere around here. So now we look at our increase and decrease. It's increasing up until negative 1. So up until negative 1, it's increasing. That looks promising. And it's concave down there as well. You can see it falls in this region. So it's going to come increasing, concave down up to our maximum point. Should still be concave down and decreasing. You can see it is decreasing now. Until 1 it's be decreasing, except for the point at 0 there. So it's decreasing and concave down until this point, the inflection point. Now it's still decreasing, but it's going to be concave up until 0. From 0 to this next inflection point right here, it's concave down again, so it's going to go like this again. And then it's concave up after that. It should still be decreasing. Yes, it decreases all the way to 1. Then it starts increasing, and it's concave up for the rest of the graph. So it looks like this. And there you go. We have our graph. Want to see exactly what it looks like? There it is. And you can see it's pretty close to what we've drawn. Exact? No, but it's pretty darn close. So the other question you might have is, well, why didn't you just graph it on here in the first place? And we wouldn't have had to do all those 16 steps. We'll talk about that in class.
La la la, la 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 la.